case of a practical current source, internal resistance is very high. Okay, so these are the definitions for ideal voltage source and ideal current source. So next is resistance. Resistance is the basic property of any material. Any object, any conductor has some resistance. This can be for insulators it is very high, for conductors it is very less. Okay, for conductors it is conductors possess less resistance. They allow current to pass through them easily. Okay, so this R, if you take a conductor, for example, if you take a conductor like this, it can have a circular cross section or square or rectangular, whatever it is. So the resistance of this conductor is directly proportional to the length. Okay, this conductor has some length. Directly proportional to length means what? More the length, more will be the resistance. Lesser the length, lesser will be the resistance. And inversely, see, this is what is known as when you chop or when you cut that conductor, when you chop this conductor, whatever the area you are getting, that is called cross-sectional area. Okay, this part is called cross-sectional area. Okay, this is denoted by A. Okay, resistance of this conductor is inversely proportional to A. Resistance of this conductor is inversely proportional to A. That means what? Lesser the area of cross section, more will be the resistance. More the area of cross section, less will be the resistance. Clear? So resistance of this conductor is directly proportional to the length of the conductor and inversely proportional to the area of cross section. Okay, this implies R is equal to rho L by A, where rho is a constant known as resistivity or specific resistance. So how do you define this resistivity or specific resistance? Resistivity or specific resistance of any material is equal to the resistance of that material when length is unity and area of cross section is unity. Can be unity means it can be 1 centimeter, 1 meter or 1 kilometer. Okay. Normally, see, resistivity or specific resistance of a given material is equal to the resistance of that material, whatever the resistance we measure, when length is unity, when the length of that material is 1 and area of cross section is unity. Okay, or in other words, the resistance offered by the unit volume of that material is called the resistivity or specific resistance. If you have a cube of any material, let us say silver. Okay, if you take a cube of silver like this, the resistance offered by this unit volume of this material, okay, that is called the resistivity, and it is constant for a given material. For silver it is having some value, for gold it is having some value, for iron it is having some value, for aluminium it is a bit difficult to remember all the values, but each material has its own resistivity or specific resistance, and it is constant for the given material. Okay, see, if you take if this is silver, if you take the same material, if you take a cube of 1 kilometer, you can imagine, I cannot draw here. Let us say if this is, imagine that this is 1 kilometer cube and this is 1 meter cube. Both are of the same material. The resistance offered by both the materials is same. Resistivity is same for both. Resistivity is same for both. Well, even if you take 1 small centimeter, same material, the resistivity of this this, when it is unity, this is 1 centimeter. This, all, the resistivity of all of the cubes is same. Okay. So this is about resistivity or specific resistance, and it is constant for a given material. Now what is current? So you know, in any atom you have nucleus at the center, and you have orbits, first orbit, second orbit, and you have outermost orbit, depends how many number of orbits and all. Okay. Here in the outermost orbit you have what is known as electrons revolving. Okay, these are known as free electrons. It is these free electrons which participate in the conduction. These free electrons participate in the conduction process. Okay, so current, if you take any conductor, okay, current is defined as the rate of flow of charge. How much charge, see, if you take any point P, how much charge is transferred across a point in a particular interval of time. If more charge means electrons, okay, if more charge is transferred across this point in a particular interval of time, then we say current is more. If less charge is transferred across a point in a conductor, then we say current is less. Okay, so current is defined as the rate of flow of charge. Flow of charge with respect to time. How much charge is transferred across a particular point in a particular interval of time. That is what is known as current, which is the most important concept in any electrical circuit. Right? So the unit for current is ampere. Unit for current is ampere. Okay. If you take a resistance of 1 ohm, okay, if you apply a voltage or potential difference of 1 volt across this, then the current flowing through this resistance is called 1 ampere. Then 1 ampere of current is defined as that current which when flowing through a resistance of 1 ohm across which a voltage of 1 volt is applied. Okay, 1 ampere is defined as if a charge of 1 coulomb, see, if you take a point P, if a charge of 1 coulomb is transferred across this point in 1 second, then this current, if a charge of 1 coulomb is transferred across this point in 1 second, then this current is called 1 ampere. So 1 coulomb of charge means how much charge? It is not a very small thing. 6.242 into 10 power 18 electrons. If these many electrons flow across this point in 1 second, then that amount of current is called 1 ampere of current. You can imagine. Is this clear? What is 1 ampere of current? Okay. So this is the definition for current and unit for current, and what do you mean by 1 ampere? So next is, if you take a charged conductor like this, now you take a unit positive charge. Here you will be having field, electric field. If you want to bring this unit positive charge from a point of infinity. See, this point is, see, if you take any point P, okay, from a point of infinite distance, that means, see, infinite means here the meaning is where the effect of this field is not felt. That is the meaning of infinity. Okay, if you want to move this charge, then some work has to be done, because you are moving that charge against the field. You are not moving along with the field. Okay, if you take negative charge, then attraction will be there, then no work has to be done. If you want to move the positive charge, then some work has to be done. Okay, the amount of work done in moving a unit positive charge from a point of infinity to this point, okay, that is called electric potential or electric potential at that point. See, this electric potential always refers to a charged point in a conductor. Okay, so whenever a body or conductor is charged, okay, if you take any point on that charged body or conductor, we can define electric potential at that point. Okay, if a body is not charged or if a material is not charged, we cannot define electric potential at that point. Okay, so the electric potential at any point on a charged conductor is defined as the amount of work done in moving a unit positive charge from a point of infinity to this point against the field. So if you take a unit positive charge which is at infinite distance from this point, infinite distance means the effect of this field is not felt. Okay, so if the amount of work done in moving a unit positive charge from a point of infinity to this point against the field is defined as the electric potential at this point. Okay, is electric potential at this point. Now if you take any 2 points, okay, P and Q, okay, supposing let us say Q is at a lower potential, this body is not uniformly charged, Q is at higher potential. Okay, let us say this is not having some irregular shape, it's not uniformly charged. The amount of work done in moving a unit positive charge from a point of lower potential to a point of higher potential, okay, is called the potential difference between the 2 points P and Q. Okay, the amount of work done in moving a unit positive charge from a point of lower potential to a point of higher potential, okay, against the field, okay, is called the potential difference between points P and Q. Okay, the unit of potential difference is 1 volt, not 1 volt. The unit of potential or potential difference is volt. Okay, 1 volt is defined as, if you take a resistance of 1 ohm and if you pass a current of 1 ampere through this, then the potential difference, this potential difference is called 1 volt. If you take 1 volt is defined as that potential difference, okay, across a resistance of 1 ohm through which a current of 1 ampere is flowing. This is called 1 volt and the unit of potential difference is volt. Okay, this is about electric potential and potential difference. This is about electric potential and potential difference. Next is Ohm's law, which is very important law. If you take a conductor, okay, Ohm's law states that at constant temperature, okay, this is very important, you are defining Ohm's law. At constant temperature, the current through a conductor is directly proportional to potential difference across its ends. The current through a conductor is directly proportional to potential difference across its ends. At constant temperature, the current through a conductor is directly proportional to the potential. See, if these 2 points are at same potential, current will not flow. Okay, higher the potential difference, higher will be the current flowing through the conductor. Okay, just like water, see, always we keep the overhead tanks at a higher height because you will get good pressure for the water to flow to the taps which are at lower heights. Okay, So higher the height, higher will be the pressure. Higher the height. Similarly, on the same analogy, higher the potential difference, more will be the current flowing through the conductor. Okay, if 2 points are at the same potential, then current cannot flow between those points. Okay, current cannot flow. Current will flow only when so this I, constant of proportionality, is I is equal to V by R. This implies V is equal to I into R. So this is called Ohm's law. Okay, V is equal to I into R. Then what are the limitations of Ohm's law? What are the limitations of Ohm's law? Ohm's law cannot be applied to non-metallic conductors like silicon carbide. Non-metallic conductors like silicon carbide. The law governing these non-metallic conductors is given by V is equal to K into I power M, where K and M are constants. Where K and M are constants. Ohm's law is not applicable for semiconductor devices like diodes, voltage regulators, transistors, etc. Similarly, Ohm's law cannot be applied for arc lamps because the non-linear characteristics of the arc produced. Okay, so these are the some of the limitations of Ohm's law. So Ohm's law cannot be applied for non-metallic conductors like silicon carbide. The VI relation is given by V is equal to K into I power M, where K and M are constants. Ohm's law cannot be applied for semiconductor devices like Zener diode. Zener diode is basically used for regulating the voltage. Okay, transistors and other semiconductor devices. Ohm's law cannot be applied for arc lamps. Okay, these are some of the limitations of Ohm's law. Next is, what is power? Mainly we are dealing with power is defined as the rate at which work is done. It is given by V into P is equal to V into I. The unit of power is watts. The unit of power is watts. What is energy? Energy is defined as the capacity to do work. Energy is given by power into time. So power, you know, it is given by V into I into T. So you get VIT. Unit of power is watt. Unit of time is seconds. So unit of energy is watt seconds. Unit of energy is watt seconds. So it is a very small unit of energy. So normally we don't use this watt seconds. Instead of that, we use kilowatt hours. Okay, 1 kilowatt hour is called 1 unit. So what is the difference between power and energy? Okay, see, if you take a bulb of 1 kilowatt, or you can take 100 watt, 10 watt bulbs, both are same. If you take a bulb of this bulb, power rating is 1 kilowatt. Okay, if you switch on this bulb for 1 hour, then the total energy consumed is what? Power into time. Okay, see, one bulb, 1 kilowatt hour into time is what? 1 hour. 1 kilowatt hour is what? 1000 watts into 1 hour. So you get 1000 watt hours. 1000 watt is 1 kilowatt. 1 kilowatt hour. 1 kilowatt hour. Okay, clear? 1 kilowatt hour. So this is also called 1 unit. Okay, in electricity bill, okay, they say that we have consumed 50 units of energy. 1 unit means 1 kilowatt. 1 kilowatt of energy. It's not power. Okay, kilowatt hour is the unit of energy. Okay, watt or kilowatt is the unit of power. Okay, so energy is nothing but the power consumed over a particular interval of time. If you integrate power with respect to time, you get energy. If you integrate power with respect to time, you get energy. The power consumed over a particular period of time. Okay, if all the electrical equipments or electrical devices are switched off, then power consumed is zero. Similarly, energy consumed is zero. Okay, see, 1 hour some devices are switched on, for some time they are off, again they are on. Okay, for some time they are on, 0 to some time, next it is off, next again from T1 to T2 to T3 some devices are on. If you sum up all the powers consumed during particular intervals of time, you will get the total energy consumed in a particular house or any other location. Okay, so this is the difference between power and energy. This is the difference between power and energy. If you integrate power with respect to time, you get what is known as energy. The unit of power is watt. If you want higher units, if large amount of power is consumed, then we use kilowatt or megawatt. The unit of energy is watt hour or kilowatt hour. 1 kilowatt hour is called 1 unit. Okay, so these are the definitions for power and energy and their units. So next is resistances in series. This is called series connection of resistors. Resistances in series. I can take 2 or 3 resistances. Let us say we will take 3 resistors connected in series. Let us call them as R1, R2, R3. V is the total voltage applied. V is the total, because of this total voltage applied, a current I will flow. Because of this current flowing, there will be a voltage drop V1 across R1, V2 across R2, V3 across R3. Okay, so this total voltage applied V is equal to the sum of individual voltage drops. V is equal to V1 plus V2 plus V3. Okay, this voltage is the total current I into the equivalent resistance of these 3 resistors in series. I will call that as RS. V1 is what? I into R1. V2 is I into R2. Similarly, V3 is I into R3. So you get IRS is what? I into R1 plus R2 plus R3. So RS is what? R1 plus R2 plus R3. Okay, if you have n resistances, then you get RS is equal to R1 plus R2 plus R3 etc. up to Rn. Okay, this is the formula for equivalent resistance of the resistors or resistances connected in series. Now you have resistances in parallel. Resistances in parallel. We will take 3 resistances. Let us say R1, R2, R3 connected in parallel. V is the applied voltage. Because the resistors are connected in parallel, voltage across each resistor will be same and it will be V. Okay, because of this applied voltage, a current I will flow here I. So here the current gets divided. I1 is the current through R1, I2 is the current through R2, I3 is the current through R3. So this I, the total current is equal to the I1 plus I2 plus I3. So this I is the total voltage divided by equivalent resistance of these 3 resistors in parallel. Let us call that as RP. I1 is V by R1. Similarly, I2 is V by R2. I3 is V by R3. Okay, V is common, so you get 1 by Rp is 1 by R1 plus 1 by R2 plus 1 by R3. If you have n resistances in parallel, in that case you get 1 by Rp is 1 by R1 plus 1 by R2 plus 1 by R3, etc. up to 1 by R. Okay. So next is branch current rule. If you have two resistors connected in parallel, R1, R2, V is the applied voltage, I is the main current or total current, I1 is the branch current, I1 is the current through R1, I2 is the current through R2. So I1 R1 is equal to I2 R2 because the voltage across both the resistances is same. So you can write this as I1 by I2 is equal to R2 by R1. You can rewrite this as I1 by I2 plus 1 is equal to R2 by R1 plus 1. So if you take I2, you get I1 plus I2 or I2 plus I1. This is equal to R1, R2 plus R1. Okay, this is I2. Okay, so this is I by I2 is equal to R1 plus R2 divided by R1. So this current I2 is equal to main current into resistance of the other branch divided by sum of the resistances. So branch current is equal to, so you should write like this, branch current is equal to main current or total current, main current into other branch resistance divided by sum of the resistances. Similarly, we can write for I1 also, branch current is equal to main current into resistance of the other branch. For this current, resistance of the other branch is R2 divided by sum of the resistances. So this is the formula or equation for branch current. Okay. So if you know the main current and resistances, you can compute the current through any branch. This is called branch current rule. Thank you.